Today, we want to look at patterns of repeated operations, specifically patterns of repeated addition, or in this case, subtraction, and eventually patterns of repeated multiplication. The reason we pick these is that we have operations that summarize repeated addition and repeated multiplication. Repeated addition is summarized with multiplication, and repeated multiplication is summarized with exponents. So they're going to produce very similar but distinct types of functions. Let's look at the three things that we need to look at, three things that we need to identify when we want to describe a pattern of a repeated operation. The three things that we're looking for when we want to describe a pattern of repeated operation are where y starts, and I'll put starts in quotes, because y goes on forever in both directions. But we're just we have to pick some point to think of as the starting point. And then we have some piece that's a description of what's happening to y. So we have the second part of the description, that's what's happening to y. And then the third part of the description is how often that happens. So these are the three things that we need to describe a pattern of the repeated operation of addition, in this case subtracting by subtraction of 4. What we want to be able to do is look at a numerical description of what's going on and translate that into a verbal description of what's going on. So we want to go from a table of values to this sentence. Now, we're not going to be very creative about this. We're going to always write the same sentence, and we're always going to write it in this order. We're going to eventually translate this sentence into an equation. So we want to be able to go from numbers to sentence to equation and also to graph, but that's really just from the numbers to the graph. So let's look at another example and identify these three things: where y starts, what's happening to the y, and how often that happens. We want to think about what's happening to the y in each step. So we start off by describing what's happening in each step. And then we also identify how big each of the steps are. So really there's something else going on above the x's, and that's the steps. X is telling us the size of the steps, but we're really going to break this down. If we're looking at numbers, we're going to break this down into a number of steps. So let's look at another example. We're going to have an x and a y. We usually like to have a 0, where x is 0 to be our start. So let's continue with that. So let's suppose that we have 0 and -3. And let's suppose that a little while later at 4, we're going to be up at 2. And then at 8, we hit 7. Then at 12, we're at 12. And then we'll do one more, 16. We'll be at 17. We want to identify three things: where y starts, what's happening to y, and how often that happens. So what we notice is that where y starts, we want to try to find where x is 0. Let's pick we don't have x equals 0, we'll pick the x that's closest to 0 and call that our starting point, although any of these will do. So I'm going to pick this as my start. I'm going to say y equals -3 when x equals 0, and that will be my starting point for the description. So y equals -3 when x equals 0. I've established a starting point in my description. Now let's look at what's happening to the y and see if we have a pattern of repeated addition. So from -3 to 2, we add 5. From 2 to 7, we add 5. From 7 to 12, we add 5. And from 12 to 17, we add 5. So what we see is that y is increasing by 5 each step. Y is increasing by 5 at each step. And that is what's happening to y. We have a pattern of repeated addition. So in our sentence, we'll write, and y is increasing by 5. So here's our description. It says it has a direction and an amount. Increasing by 5 is one step, but I want to highlight the increasing and the amount, 5. Now if we look up at the x's, we go from 0 to 4, and then from 4 to 8, from 8 to 12. Each of the steps is 4 units long. Each step is 4 units. So that's how we describe how often we see the change in y. So y increases by 5 every 4 units. And there's a sentence. There's a sentence describing what's happening in the table of values. We also want to be able to do this the other direction. If I come up with a description, we should be able to come up with what values will fit that description. So like always in math, we have to learn things backwards and forwards. So let's write a description. Let's suppose that y equals 53 when x equals 0. And let's suppose that y is decreasing by 11 every 5 units. So I've got all the things that I would want to build a numeric description of what's going on in this function. Let's use it to construct a table. And just fill in some values. So y is 53 when x is 0. Let's use that as our starting point. When x is 0, y is 53. Let's make a note of what's happening to the y. Y is decreasing by 11. So in each step, will decrease by 11. So 53 will decrease by 11 to 42. And then we can continue the pattern of decreasing by 11. So 42 minus 11 is 31. 31 minus 11 is 20. 20 minus 11 is 9. And here we see this pattern of decreasing by 11. This pattern should continue in both directions. So we should be able to think about what's going on before we got to 53. What should we subtract for, what do we end up with? If we ended up at 53, what did we subtract 11 from? And so we could go backwards. If we're subtracting 11 from left to right, we'll add 11 from right to left. 9 plus 11 is 20, plus 11 is 31. So we must have been here at 64. 64 minus 11 is 53. Now, this is just based on the description. Y is decreasing by 11. The every 5 units tell us how often this is going to happen, tell us how big each step is. So each step will be 5 units long. So 0 to 5, 10, 15, and 20. And if we go backwards, When x is -5, y is 64. So there's our step size of +5. Let's look at an example where we don't know what's going on when x is equal to 0. Let's have a different description. I want to once again write a description, and then we'll try to come up with I'll write a sentence, and then we'll come up with a table of values just based on what we see in the sentence. So let's look at another example. Let's suppose that we have some strange information like y is equal to 27 when x equals -2. So we don't know what, we're going to pretend that we don't know what's going on at 0. And let's suppose, let's see, we just did it in a decreasing one. So let's say y is increasing by 8 every 3 units. So we've got the 3 things that we need to write down a table. We have a starting value, we have a start, we have what's happening to y, and we see how often that happens, the step size. Let's use this to make a table of values. I'm going to put my starting value. Y starts off at 27, but this doesn't happen when x is equal to 0. This happens when x equals -2. And we're going to note that y is increasing by 8. So each step, we're going to increase by 8. So 27 plus 8 is 30 something. And then 35 plus 8 is going to be 43. 43 plus 8 is 51. 51 plus 8 is 59. If we want to go backwards, we have to think what plus 8 is 27. And we can figure that out by doing 27 minus 8. If we're adding from left to right, we'll subtract from right to left. 27 minus 8 is 19. And we can keep going. We can take another step backwards since we have space. 19 minus 8 is 11. Notice that maintains a step size of, change in y of plus 8. 11 plus 8 is 19. 19 plus 8 is 27, and so on. Now we started off at -2, but the step size is every 3 units. So if we started off at -2 and add 3, we'll be at 1. And then 1 plus 3 is 4, plus 3 is 7, plus 3 is 10. If I want to go backwards, if we're adding from left to right, we're subtracting from right to left. So -2 minus 3 is -5. -5 minus 3 is -8. So we've taken this sentence that describes what's going on in our function and written down a bunch of points that fit this description. So we see we have a pattern of repeated addition. So we have these patterns of repeated addition. This raises a question. We know that multiplication is repeated addition. So where does the multiplication enter into it? If we have repeated addition, we should be able to find some multiplication. So this raises a question. I've identified this as a pattern of repeated addition. I say we're adding 8 a bunch of times. So if this is repeated addition, where's the multiplication? Where's the 8 times something? We should see 8 times something because that's what adding 8 a bunch of times should be summarized as. So let's take a look at a different example. I'm going to reduce my step size to 1 so we can see where the multiplication comes into it. Let's look at an example. Let's suppose that y is equal to 20 when x is equal to 0. I'm going to reset my starting point back down to a 0. And let's suppose that y is increasing by 3 every 1 unit. So I'm going to make the step size equal to 1. So here are the things that we need. Y is 20 when x is 0. That's where we start. We have a part of the description of how y is changing. Y is increasing by 3. And we have the step size every 1 unit. Y is increasing by 3 every step, and every step is 1 unit long. Let's make a table of values. Let's make a table of values. Describing what's going on. So y is 20 when x is 0. So I'm going to leave a couple spaces. So y is 20 when x is 0, and y is increasing by 3 every 1 unit. So plus 3 is the change in y, plus 1 is the change in x. So we'll go from 20 to 23 to 26 to 29 to 32 at 1, 2, 3, and 4. We should go backwards a couple of steps. So if we ended up at 20 and we added 3, we must have started off at 17. And before 17, we must have been at 14. And that should have been at -1 and -2. So we still see an increase of 3 every 1 unit. So when we go from 23 to 26, we've taken 2 steps. So from 23 to 26, we've added 3 2 times. From 20 to 26, from y equals 20 to y equals 26, we have added 3 2 times. That is, we've started off with 20, and we added 3 2 times. Start with 20 and add 3 a bunch of times. Start with 20 and add 3 2 times. 2 is the number of steps. Start with 20, add 3, 2 times. From y equals 20 to 29, we started with 20 and added 3 3 times. We've taken 3 steps. So from y equals 20 to y equals 29, we have added 3 times. So we start with 20. We started with 20, and we added 3 times. Here we start with 20, and add 3 times. If we go to 24, to 32, we have added 3 4 times. We've taken 4 steps. From 20 to 32, we've added 3 4 times. We've taken 4 steps. So 2 times, 2 steps. 3 times, we've taken 3 steps. 4 times, we've taken 4 steps. Four times represents the 4 steps. And we would write, to write in algebra what we've done, we've taken 20, and we've added 3 4 times. Start with 20, add 3 4 times. There's where the multiplication comes into it. We take what we're doing to the y and multiply by the number of steps. So we take the start, we add the change in y, and we multiply by the number of steps. Start, add the change in y, and multiply by the number of steps. What this is going to look like, we're going to want to encode this. Now, writing start every time is cumbersome. Writing change in y every time is cumbersome. And writing number of steps every time is cumbersome. So, as mathematicians are wont to do, we're going to give these things names. So this is going to show up as, we're going to call the start, we're going to say, let's start at the y-intercept and call the y-intercept 0, b. And let's add the change in y, which is going to be at least part of the slope. Oops. Here I am trying to encode things. And I'm not encoding things. So what this is going to look like is we're going to write the start as b, and the change in y is going to be some kind of slope. And the number of steps, we want to add m a bunch of times, so we just multiply by the number of steps. And so this is how the construction y equals mx plus b, why y equals mx plus b is so useful. This construction says start with b and add m a bunch of times. That's all that's going on when we write y equals mx plus b. It's a pattern of repeated addition that's being summarized with multiplication. This times x is the summary of repeated addition with multiplication. Start with b. Add m a bunch of times. So, as usual in this class, I'm not doing anything new. Even though yesterday I said, let's start with something new. This is not new at all. This is just y equals mx plus b, but where y equals mx plus b comes from and how it fits with our idea of operations and how the operations interact. So we've introduced something that may be familiar, adding m and calling it m, because m is the letter that we use for the slope. Makes sense to use m as slope because m does not appear in the word slope at all. I've always wondered where m became the slope. And I don't know enough languages to translate the word slope into other languages. And I haven't been curious enough to just kind of like Google it. But m is the slope. Or should I say, as I'm going to soon, m is the slope in purple. And we know some things about the slope. We may remember some things about the slope. We know that there's an R&R definition of the slope. The slope is rise over run. So there's a lot of things that might be triggered in our memory when I use the word slope. When I write things like y equals mx plus b, that could trigger some memories of slope, and that might remind us of slope is rise over run. We also might remember something like y2 minus y1 over x2 minus x1, but if we don't remember how to construct a slope, it's because we relied too much on y2 minus y1 over x2 minus x1, which is a formula for slope, but it's terrible. It's like the quadratic formula. It's terrible. Don't do that. It's like PEMDAS. Slope is rise over run, the change in y divided by change in x. But all we're doing is a pattern of repeated addition. When we establish a linear function like this, we're saying start with, when we write y equals mx plus b, we're saying start with b and add m a bunch of times. When we summarize the slope as the rise over run, we're saying do increase by m with a step size of 1. It's very limiting when we do things like that. But let's look at an equation, translate it into a sentence, and then write a table of values. So let's suppose that we have an equation. Let's suppose that y is equal to can't remember what I used in the last one. 3. Oh, I never even translated the last one for you. How you guys let me get away with this? So in this table of values, we see that y is equal to 20 when x is 0, and y is increasing by 3 every 1 unit. So we can translate this by saying y should start off at 20, and we should add 3 a bunch of times. So here's an equation for this function. If I plug in 4, when x is 4, I go 3 times 4 is 12. 12 plus 20 is 32. Because we take 20 and add 3 4 times. If x is -1, take 20 and add 3 -1 times. So subtract a 3 and end up at 17. When x is -2, subtract 3 2 times. 20 minus 3 is 17, minus 3 again is 14. X is the number of steps we should take. And that's it. So y equals 20 plus 3x. Let's look at another equation and translate it into a sentence and then write a table of values. Oops, we got smudged a little bit. So let's write an equation. Let's suppose that y is equal to -13 plus 5x. So what this equation is asking us to do, the fixed value, the one that doesn't have the x attached to it, is the -13. So this says start at 13. So we can write that as y equals, -13 when x is 0. Notice that the x is all by, if we plug in 0 for x, we just have the -13. So y is -13 when x is 0. And y is, it says plus 5. So y is increasing by 5 every 1 unit. What this equation is asking us to do is start with -13 and add 5 a bunch of times. But saying a bunch of times is way too casual for a math class, so we say multiply by x. Now we've encoded that whole thought into start at -13 and increase by 5 every 1 unit. So table of values style. Y is -13 when x is 0. And we should increase by 5 every 1 unit. So when x is 1, -13 plus 5 is -8. When x is 2, we've increased by 5 again to -3. When x is 3, we increase by 5 again to 2. When x is 4, we increase by 5 and end up at 7. If we want to go backwards, instead of increasing by 5 to the right, we'll decrease by 5 to the left. So -13 will go down to -18 when x is -1. And when x is -2, we'll decrease by 5 again to be at -23. So there's a bunch of values that fit this equation. And we can check some. If we plug in 4, if we plug 4 into our equation, we get -13 plus 5 times 4. Order of operation says multiplication before addition. So 5 times 4 is 20. -13 plus 20 is 7. So things are checking out. If we try some other values, y is equal to -13 plus 5 times 3. So -13, the order of operation says multiplication before addition. So 5 times 3 is 15. -13 plus 5 plus 15 is 2. Checks out. If we check out values on the other side, y is equal to -13 plus 5 times -1. Multiplication goes before addition unless parentheses say otherwise. Plus 5 times -1 is -5. -13 minus 5 is -18. So it seems that our values are correct. Now, we could have generated the values in the table by plugging in all the x values, like some machine, but we're not trying to be a machine. We're trying to understand the connection between the sentence, the numbers in the table, and the equation. Any questions? All right. The next step is to note that slope is rise. We're going to play with the idea that slope is rise over run. We're going to abbreviate slope with m, and we're going to think of it as rise over run. And I'm going to make sure we color code it. Where rise, we're going to call rise is what's happening to y. And the run is the step size. We're going to make one number, take the rise over the run, where the rise is what's happening to y, and the run is how often that happens. That's the step size. What this is going to mean is the change in y divided by the change in x. So this is going to be the change in y. The rise is the change in y, and the run will be the change in x. And we are not going to think about the slope formula, because learning things by formula is why we'll forget them now. We're also going to recognize that the slope is a proportion, and it's just since it's multiplication representing repeated addition, we're going to see that the slope is proportional. So increasing by 5 every 1 unit is going to be the same as increasing by 10 every 2 units. So we're going to play with the proportion that we get to in the slope. All right, that's going to do it for today. I will see you all on tomorrow. Everybody have a nice day, and thanks for playing.